Everybody, let's get things started off on the right foot and on time here. My name's Chad. I'm in the first session chair, and we're going to begin with Adam Leroy telling us about observing the multiple phases of the ISM in nearby galaxies.
Can you hear me? That should be electric.
That's what's important.
Which means you can't cut me off. No.
Tackle you. Take it away.
Cool. So thanks, and I super appreciate the chance to speak. And I am actually super looking forward to also getting to speak and then pay attention to the extremely exciting agenda for the next few days. So what I'm going to talk about is observing the multi-phase ISM in nearby galaxies. I'm not going to talk about the pictures on the screen right now, but since this is what I've been working on recently and they're beautiful pictures, if you have interest in looking at nearby galaxies at sort of arc-second resolution in CO, I'm delighted to chatter about this at coffee breaks. This is where a lot of my effort has been going recently. And just as an advertisement, ALMA is extremely good at doing this kind of thing. But what I am going to talk about today, and I'm going to try and take the sort of broad and wide approach to this, is observations of nearby galaxies that address the sort of main theme of this conference, which is observing the multi-phase ISM. And so like I said, I'm going to try and go broad and wide, where I say a few words about a bunch of topics and maybe try to stimulate some discussion, and in particular across some of the Milky Way thinking with extragalactic thinking over the rest of the week. So I'm basically aiming to talk about 4 areas. So phase balance in the atomic gas, density structure in the molecular gas, a very simple form of chemical structure in the molecular gas, meaning the balance between essentially H2 where you have bright CO and H2 where you don't have bright CO, so the so-called CO dark H2. And then the balance between atomic and molecular gas. And I, of course, cannot do justice to any of these topics, but that's the overall plan. So I'm going to start with what might be the hardest of these to actually look at extragalactically, although is highly thematic for this conference. So we're going to hear about this a lot more later in the week. But hopefully everybody in the room appreciates that neutral atomic gas comes in different flavors. So you have warm and less dense gas, you have cold and denser gas, and depending on your thermal pressure, you may have both phases at the same time. You may also have unstable gas sitting in the intermediate regime. So depending on your thermal pressure, one of these may be allowed, both may be allowed, and it would be fascinating to understand how the breakdown between these phases maps to environment in galaxies and maps to location in galaxies other than our own. So essentially, what we would like to understand is, to put it in a nutshell, where do you get a CNM? How is getting a CNM linked to star formation? And how do both of these things link to feedback processes? But it turns out that this is really hard. And the short version of the reason is that it's hard is that the work that folks like Carl and Snezna and Claire have done relies on having bright background point sources. And to some degree, those map to essentially the aerial coverage that you have available in the system that you're interested in. And other galaxies are small on the sky, which stinks. So it means that other techniques have had to be deployed to chase after the cold neutral medium in galaxies. And by far the most common of these, because it's a thing that you can do no matter what if you have an H1 data cube, is to treat the emission line profile and attempt emission line profile decomposition. And so I'm showing here what I think is the sort of latest and greatest version of this type of study, an illustration of the technique from Warren et al. Using the VLA angst survey in 2012. And the idea here is that you take a 21 centimeter profile and you attempt to fit it with a Gaussian, and sometimes a Gaussian doesn't do a good job, and you need a couple of Gaussians. And this idea goes back to Lisa Young's thesis in the 90s, and it's been deployed a number of times in the intermediate range. And when you have a second Gaussian that you need, if that Gaussian has a narrow line width, then you would argue that this narrow line width is indicative of having at least a cold phase and possibly explicit CNM. Although the direct line widths in questions are not always exactly the thermal line width of the CNM. So, people do find these narrow line components using emission line analysis, but they're not found nearly as extensively or with nearly as much flux as we think the CNM actually should have in these galaxies. So essentially, just attempting profile decomposition in H1 maps of other galaxies does not give you the same amount of CNM that you know that we have in the Milky Way from absorption studies. And so there are illustrations here highlighting in red in some of the dwarfs in the VLA angst survey or in contours in this local group dwarf on the right, locations where people have found a cold, narrow phase. In brief, the Warren study found that they could place a hard lower limit of only a few percent on the CNM in these galaxies, which we know from work in the Milky Way is far too low. You can understand why this would be, which is essentially that you need your CNM to be syncing up and giving you a coherent line profile at the resolution of your H1 cube. And so if it's spread out and there's other things contributing to the line width, you won't get a cold phase showing up as a simple component in your H1 emission spectra. And so there are hints of resolution biases in some of the work that's been done. But this is mostly a tale of frustration looking for these things, or at least lower limits. The other analogous approach that has been taken using emission is to simply say, oh, well, we know that the cold H1 has significant opacity, and so that should mean that to some approximation, the brightest pixel along any line of sight in a given H1 emission spectrum maps to something like an upper limit on the amount of coherent cold H1. And so this is an argument laid out by Brown in the late 90s and not pursued very much since then. But the idea is that the H1 brightness temperature gives you some constraint on the presence of a cold phase. You can immediately see all of the additional sort of counterarguments that you could make. But again, this is sort of struggling against the extreme difficulty of actually finding cold H1 in nearby galaxies. And so the specific claim that came out of this study was not so much a hard number on the abundance of the CNM, but the statement that signatures of high brightness, potentially opaque, narrow line width cold H1 appeared to disappear at around the same place that star formation disappeared when studying high resolution VLA maps of nearby galaxies. And so there's a claim here that the CNM may be pervasive where you actually find star formation in galaxies. So I think that this point is actually interesting and perhaps not as widely appreciated. Maybe the Milky Way community appreciates it entirely. I think the extragalactic community does not appreciate it as much. But related to this idea that the CNM may be this, the CNM shows significant opacity in our own galaxy, not all of which is just that we're sitting on our side, is this question of how much of the H1 is missed by 21 centimeter maps. And so this is, again, work by Brown and collaborators over the last few years, arguing, again, based on line profile analysis. And you can sort of see what kind of line profile analysis is being done here. You fit the emission lines, and you say when they look top hat, then that's indicative of opacity. One can certainly ask whether that's the ideal way to chase after this. But the effect claimed is significant. It's something like 30% of the H1 is missed, but crucially, 30% of the H1 is missed by these 21 centimeter emission line maps in the places that you really care about it. So in star-forming filaments, distributed in coherent, cold, dark structures. Whether this specific claim holds up or not, this amount of opaque 21 centimeter emission is certainly allowed by comparison to the damped Lyman alpha systems. That's an explicit comparison that they do in arguing this work and goes back to Zwan and collaborators. And so their argument is that something like 30% of the H1 is missed in 21 centimeter emission line maps of galaxies, and that this is a very interestingly placed 30% of the emission. That is, for those keeping score at home, essentially equal to the entire molecular phase in these galaxies, dwarfing it in the case of the dwarfs. So this is this opacity of the cold phase is an important open question. Ultimately, of course, what we would like to do is to do the same kind of analysis on other galaxies that's been done on our own galaxy that we'll hear about later in the week. And that's to use emission lines, or to use absorption line studies, which gives you the sort of best probe of the physical state of the cold gas. So far, this is only able to be done on the biggest galaxies on the sky. And this is a topic that, as far as I know, was sort of run to ground in the late 90s and early 2000s by Dickey and collaborators. And you can see that what they've managed to do is absorption line studies of something like 100 background sources behind the local group galaxies, which are the biggest galaxies on the sky. And there are differences found. The Small Magellanic Cloud, for instance, you can see here, has a relatively low fraction of cold gas. But mostly, I think this is indicative of where we would like to go in the future. There's one other way that you can imagine tracing this, which is that the emissivity of the atomic gas is much higher in C+ when it's CNM than it is when it's WNM. Herschel and Sophia have been mapping C+ across many galaxies. So far, this has not been a main topic of these studies, because the places that have been targeted have not been dominated by atomic gas as much. But this is an area and a type of analysis that potentially, moving forward, could be a fruitful way to distinguish, to some approximation, C plus divided by 21 centimeter column density tells you CNM fraction. That's not exactly right, but it's close. So of course, the prospects here are awesome, but rely on the sort of next generation 21 centimeter instruments. And so the elephants in the room for seeing this kind of thing improve are certainly going to be the SKA, where background, you'll just move along the point source spectrum in terms of what's accessible to do absorption studies. And you should be able to deploy this background absorption, deploy 21 centimeter absorption against background sources much more widely. But you'll also see improvements in this direction with the sort of intermediate surveys, Mongoose, ASCAP, and Aperitif, as you get deep absorption or deep measurements on many sources on the sky and the ability to deploy these emission line analysis techniques widely. So let me shift gears to a more optimistic topic, which is something that we're making enormous progress on right now, thanks to advances in sort of millimeter instrumentation over the last few years. So H1 isn't the only type of gas that shows a range of phases. So we also know that molecular gas shows, in particular, a very wide range of densities, even within an individual molecular cloud. And thanks to advances at its sort of millimeter wave ability to detect faint lines over the last few years, we're now able to map not only the sort of bright CO gas that traces, that to some approximation traces all of the gas, but we're also able to map lines that have density sensitivities to much higher densities. And so what I'm showing you here is emissivity as a function of collider volume density for some now accessible extragalactic lines using a radix calculation. And so what you can see is that if you get a suite of these lines, you have some sensitivity, in particular as you watch them vary across a galaxy, you have some sensitivity to how the density distribution is going to change inside of galaxies. And this is something we're able to do now, and we're specifically able to do very effectively for the last few years by deploying generous allocations from the ARM 30 meter, from ALMA, and soon we hope to be able to be using GBT with this new Argus receiver coming online to do this sort of in absolute production mode. But what I'm showing you here are maps of these higher critical density lines. So in particular here, I'm showing you HCN and HCO plus, tracers of high density gas, compared to CO and a few nearby Messier galaxies. So we're in the process of compiling these kinds of maps for something like 15 galaxies. And you can see the issue is that even using state-of-the-art facilities, these lines are incredibly faint. So there's something like 30 times fainter than carbon monoxide emission, meaning that for an equivalent map, 1,000 times the time, or better facility, but still extremely expensive. And so we are able to get these maps. The signal to noise is still sort of pushing the capabilities of the instrument, but this means that it's new and exciting. And what we find is that the physical state of the gas does change. So specifically, gas gets denser as you move to high surface density, high pressure regions of galaxies. And so what I'm showing you here are dots that show you regions inside of galaxies. In blue, there's results from a paper by Antonio Ucero last year. So you're looking at 30 galaxies and sort of twiddle kiloparsec regions. And then in gray and then binned into red is full disk mapping of M51, which is the first of our sort of full disk maps to be published earlier this year. And what you see is that the HCN to CO ratio, a density tracing ratio, increases as you move to high density parts of galaxies. And so it does this in a consistent way across a set of nearby star-forming disk galaxies. And you see, and essentially this gives you a handle on, oh, the density of the gas is increasing. But we actually get a suite of these lines, and we're trying to do something better than simply using a single HCN to CO ratio. So in principle, we get an ensemble of measurements that span a range of density sensitivities. So I showed you emissivity as a function of density when I started this section. And what you could see is that different lines are excited at different densities. And so what I'm showing you here is that we can arrange these this sort of full suite of lines into a line ratio pattern. So here for M51, I've sorted the lines on the x-axis by critical density. I've colored the points by radius. So these are radial bins with line ratio patterns sorted by critical density. And then I've divided an overall pattern out on the right. And you can see that there's a sort of flaring distribution where the high critical density lines show strong dependence on environment. Their ratio to CO shows a strong dependence on environment, and the dependence of the smaller, the dependence of the lower critical density lines on environment is weaker. And we've done this at least somewhat more rigorously using LVG calculations, but I think the cartoon is the easiest way to understand this. So an easy way to understand this is as the effect of sliding a log normal or some other similar density distribution across a series of lines that have step function emissivity thresholds. And the idea here would be that the high critical density lines are showing a high variability in how much they emit because you're moving through a very steep part of the tail, the upper tail of the PDF. Whereas something like CO integrates from low densities up to high densities. This is a point that has been made a few times in different contexts, specifically interest in the slope of the star formation scaling relation by Narayanan and Krumholtz and Thompson. But I think it's a more powerful general point, which is that the line ratios of these things, particularly their variation, so that you normalize out potential emissivity or potential abundance variations, tells you potentially about the changing density distribution. And if you can make that density distribution parametric, you can over-constrain it with a number of line ratios. So what about star formation? Star formation tracks dense gas, right? So this must mean that these regions of galaxies are getting much, much better at forming stars. So as I expect the Milky Way folks are familiar with, that's not actually entirely true here. So instead, what we see is that the dense gas that we're seeing become more prevalent as we move to the high pressure centers of galaxies is actually worse at forming stars than the dense gas that we would find in the outskirts of galaxies. So this resembles results found contrasting Gould's belt and the Milky Way center that, for example, Longmore, Rathborn, Mills, and collaborators and folks like that have been doing in our own galaxy. But what you can see here is that this is a general trend. So the infrared to HCN ratio on the y-axis here decreases as you move from the left, which are lower pressure parts of galaxies, into higher pressure parts of galaxies on the right. So high stellar surface densities, high molecular to atomic ratios correspond to lower ratios of star formation to dense gas. And this is, again, potentially easy to understand in cartoon form. If you viewed clouds as having a somewhat fixed dynamical state, so they're all marginally bound when they start, then only the high density parts of an individual cloud will actually be strongly self-gravitating and lead to sort of runaway collapse in star formation. So if star formation is fundamentally about density contrast with the cloud instead of about any absolute density threshold, then you would expect that in regions that have a high mean density, then you would expect the highest density gas to actually have higher absolute densities than you would in, say, a low density region like Gould's belt. So the future here is bright or faint. As I mentioned, we're deploying fantastic new capabilities especially the Argus array on the GBT is going to be great over the next couple of years. ALMA is fantastic and an amazing machine to do this. And eventually, to put this into true production mode, I encourage you to tune into discussions about the possibility for a next generation very large array, which would be a machine that would be phenomenal at doing this kind of science and would make this routine in a way that CO is routine now, but that this is still not routine with ALMA. So I've discussed density, but molecular gas also separates chemically. And so a key aspect of this that has actually had a lot of attention over the last few years has been a very simple chemical separation, which is the breakdown of the outer part of a cloud into regions where the gas is molecular but does not have CO, and regions where the gas is molecular but does have CO. So the point here is that a general calculation or general suggestion of PDR calculations and things that have been, and something that has been demonstrated in studies of local clouds by folks here, is that there is a substantial layer of CO dark H2 engulfing the things that emit brightly in CO in a local cloud. And so H2 persists as CO is photodissociated. This region has magnitude maybe 30 to 50% of the total gas from Planck or Fermi calculations in the Milky Way. But because this effect is at some level, just that you need to build up a certain amount of additional shielding to keep CO around, as you move to systems with very low dust to gas ratios, the amount of gas mass that you need to accumulate to build up the same amount of additional shielding goes up. And so there's an expectation that this CO dark gas layer should be enormous as you move to low metallicity clouds. And when you hear people talk about the metallicity dependence of the CO to H2 conversion factor, this is the dominant effect. It's not necessarily C and O disappearing. It's the need to build up a huge additional shielding layer. Other people might have other opinions on this, but that would be my overall characterization of this. And you can see a cartoon of this as you move a cloud, the same cloud from lower to higher metallicity here. So people have chased after this in a number of ways. And usually the way that you would chase after the CO to H2 conversion factor is to measure the CO, which is fairly easy, and estimate the H2, which requires some sort of hand waving. So this has been done with IR rotational lines. Dust, I would say, is the current preferred method to trace all of the gas. You can also chase after the mass of the molecular gas using dynamical measurements, or potentially absorption, although there's a bias against getting UV absorption in the places that you really care about. And so people have done this. So I'm going to tell you about what people have done, but a simpler prediction to test in the first place is that at very low metallicities, the CO emitting surface, a corollary of this, should be pushed deep into molecular clouds. So ALMA, it turns out, is a fantastic machine for observing small clumps of CO in very local galaxies. This should not be a total surprise. But over the last few years, this result has come out in a few forms. I'm showing you what I think is the prettiest version here, and I'm somewhat biased to my former student. So a number of times people have looked at local group galaxies and shown that the CO emission is confined to only a few parsec-sized clumps. So the sort of seminal result on this is a paper by Rubio in Nature last year looking at WLM. I'm showing you here the local group dwarf galaxy NGC 6822. So this is about a fifth solar metallicity. And the resolution here on the CO maps on the left are about 2 parsecs. And so what you see is that things are highly structured at a couple parsec resolution, so pushed far in compared to what you would expect for a local galactic molecular cloud. So the CO is clumped and confined, but that doesn't immediately tell you that you have a ton of H2 sitting outside it. To chase after that, dust has been the main way that we've done this over the last few years. And I'm showing you here results for the CO to H2 conversion factor as a function of metallicity using dust. So for places that we have dust and think we can infer H2 after subtracting the H1. And what you see is that there's a very high implied amount of H2 relative to the CO as you go to very low metallicities. So look at the left of the plot, contrast with normal galaxies, and you would say that you're going up through the roof in terms of the amount of H2. But there's also enormous scatter. So this is consistent broadly with PDR calculations, but it's not yet a precision prediction. So we're able to say, oh, there's a lot of dust compared to what we would expect from the CO, even after we account for the H1, but we can't yet say, use this exact conversion factor as a function of metallicity. So I want to briefly suggest that a way that we could potentially do this more productively is actually to separate the problem into parts. So we made this argument in a couple of papers by a student that I've been working with at UVA, Cheljong Lee. So one's published, one should be submitted soon. And basically the idea that we suggested is that perhaps you can think about the PDFs of clouds, the dust to gas ratio, the dependence of CO emission on dust shielding, all as potentially somewhat separable parts. It's not a given that this has to be the case, but what makes us think that this is potentially a fruitful way to go is that when we go measure the CO intensity at a fixed dust shielding layer, so at a fixed dust column density, it appears to be about the same in the Small Magellanic Cloud, the Large Magellanic Cloud, and the Milky Way. So that's across a factor of 5 in metallicity. Having about the same amount of dust gives you about the same amount of CO emission. So the implication there would be that this gives you a tool to imagine taking a distribution of gas column densities, turning it into a distribution of dust column densities using a dust to gas ratio, applying the AV to CO relation, applying the CO emission at a given column density, and predicting the amount of CO emission you would expect from that cloud dropped into that dust to gas ratio. And so we did this, and there's 2 sort of quick takeaway points. So the first is that it really matters if CO has some threshold in AV for emission, which it turns out is not actually all that well measured. People have tried this really hard, and you quickly run into the backgrounds even in the Milky Way. And I think we'll hear about this more later this week. But the other point is that the cloud that you put in and the CO dependence on AV that you put in becomes an extremely sensitive input, or sorry, the output of the CO to H2 conversion factor is extremely sensitive to those inputs as you go to even modestly low metallicity. So even down at something like the SMC, you're really grabbing the dog by its tail in terms of the amount of gas that effectively emits CO. So you're really only talking about the high column density end of the PDF emitting CO, which means that, yes, this is a way to trace molecular gas at low metallicities, but it's hardly an agnostic tracer of the total molecular medium. Future here is also great. ALMA, as you saw, can make maps of CO at very high resolution. And it turns out HST although it's been up there for 30 years, actually has amazing new legs, especially with the Wide Field Camera 3, for making dust maps of nearby galaxies by just looking at extinction. So this is something Julianne Delcanton did a beautiful paper in M31 on last year, and Karen Sandstrom is working hard on in the SMC. So I encourage you to check those out as they show up. So let me close by saying a couple words about the balance between the atomic and molecular phase, which I've discussed separately. So this is an enormous topic. It'll be talked about a number of times during the conference. But I want to show you results that we're sort of working on now that I think are somewhat new and something that you only can do in external galaxies. So to first order, molecular and atomic gas separate and show a strong dependence on locations in galaxies, with the sense that the molecular gas is confined to the inner high surface density, high gas column density parts of galaxies. Molecular gas is more abundant in high mass galaxies, in high metallicity galaxies. And you end up with a situation that looks like this. This is just an example CO map and H1 map for a reasonably typical nearby galaxy. This is the corresponding radial profile. And what you see is that the center of the galaxy is highly molecular. This is where the stars are forming. And H1 sprawls out over the low surface density part of the galaxy. So to first order, there are a number of theoretical explanations of this. To first order, they generally treat the total gas column density as the driver for the molecular to atomic ratio. So what you can see here is that the second order effect that they call out, and this includes papers by Krumholtz, by McKee, Sternberg, and a number of other folks, the second order dependence that folks would call out is the dust to gas ratio, the metallicity dependence. And what I'm showing you here is the H2 to H1 ratio for a sample of 25 galaxies at sort of kiloparsec resolution, with the H2 to H1 ratio as a function of total gas surface density on the left, and the dust surface density as a function of total gas surface density on the right. And I've cross-colored the plots so that on the left, dust to gas ratio is color, and on the right, molecular fraction is color. And what you can see is that there's actually a three-space relationship between these things. So that at a fixed gas column density, you have a higher molecular to atomic ratio if you have a higher dust to gas ratio. So we can do this in somewhat more detail by simply distilling these trends into, we can treat the total gas column density as the overall independent variable, distill both of these relationships into median trends, and measure the offset logarithmically from these trends, and then compare the residuals about the trends in molecular gas to the residuals about the trends in dust to gas ratio. And what we see is this. So this is a steeper than linear dependence of molecular fraction on metallicity, implying that metallicity is a very strong effect. It convolves the conversion factor and the molecular fraction relationship. But I think this is new. This has not been directly measured, certainly locally, before. So I think this is potentially exciting. The stellar surface density remains extremely important. I won't talk about it, but I want to emphasize that this does not undermine the idea that the stellar potential well plays a key role. So I blazed through this far more quickly than I thought, despite the fact that I showed you guys 40 slides. So this is basically what I've stepped through. I'm happy to take questions. I think I opened many more questions than I could potentially answer, but thank you very much. Yeah.
Questions? Are we going to be running mics around here? Excellent. All right, so you can wait with your hand awkwardly in the air. Katie?
Really great talk, Adam. So I feel like I might be opening a can of worms here, but I noticed on your slide where you were showing the dense gas maps of galaxies.
Yep.
You were actually showing 2 Virgo galaxies.
Yes.
So
Don't know yet is the answer to
yeah.
environment, but go ahead.
Well, we found in the Atlas 3D galaxies that we had early type galaxies that had much higher 13 to 12 CO ratios than field elliptical galaxies or early type galaxies, and I was wondering exactly.
So we have been doing the CO isotope log analysis here, and it looks normal for these galaxies. These are spirals, right? And so in the inner parts, we've specifically been doing the 13 CO to C18O ratio, and that number looks pretty normal for these guys. And so my off the cuff guess would be that they're spirals because they're on the outer parts of Virgo, and so maybe less environmentally processed. I mean, there may be a morphology density relationship thing here, but we have about half Virgo and half not. We have not hashed them formally yet. And so this will be interesting to actually check out.
You just mentioned in your last slide, there was the second point, I think, about the density fluctuations, right? And you mentioned log-normal distribution.
Yep.
But log-normal distributions are notoriously difficult to distinguish from power law distributions.
Yeah, that's right. And
the implication for star formation can be enormous.
yes.
From power law spectrum of turbulence, compressible turbulence, you might expect a power law rather than log-normal distribution. So log-normal, is it just assumption based on convenience?
Yes.
Was there any attempt, and is there any forthcoming attempt to really decide, is it a power law or log-normal?
So I think that we are not in the best position to distinguish, but I think in the sense that, what I should say, I used this in two places, right? So I used it in the CO to H2 conversion factor, and I used it in the density line, the line ratio distribution as a function of density. So for both, the trick will be to push to the highest possible densities and ask whether the log normal predicts a smaller number because of the different sort of falling as you go to very high columns. And so I think there are prospects to do that. So I think we can look at the high density tail in both cases and ask, is this consistent with log normal? I think the low density end is very hard extragalactically. And so we are definitely aware of the degeneracies between these. And I think the other thing you can do is just ask, does the under the hood assumption affect the output results? Does log normal versus power law? It's very good for us to have one or two free parameters and define the density distribution in that way. But we're not deeply wedded to the log normal versus power law. And I think it's good to understand when it makes a difference.
May I just say a short word of warning? Because now log normal is very often favored by numerical simulations. But they do not have, they have low Reynolds numbers, and they do not have a power law spectrum of turbulence.
Yep.
So I think log normal and power law should be equally treated with the eyes wide open on both possibilities. Otherwise, we can mislead ourselves.
I think that's extremely fair.
Thank you.
Yep.
Well, he asked almost my whole question, so he left me about 10% of it. But continuing with the log normals and power laws, you mentioned the possibility of sliding log normals.
That's right.
And so my question was, can that be told from a single power law?
I think we have not done the calculation yet, but it's clear that it would produce a similar trend because you need a falling density distribution. And so we will do this. Yes.
So I had a question about your the environmental dependence of the critical density tracers, right? And so another word for environmental dependence is chemical abundance, right?
Right, and so this is, I don't have a great answer to this except that we divide out the overall trend, and I showed you guys a normalized variation. So it has to be internal variations in the chemical abundance, and this is why we're trying to use an ensemble of lines. But if the abundances of the molecules vary or their optical depths vary, we're in trouble. And so we're trying to measure all of these things, but chemistry matters.
Yeah, I think now you've got two axes, right? So you've got the critical density, then you've got the abundance, and there's a third axis, which is the sensitivity of the observations. Because we know from looking at nearby molecular clouds that if one observes something like N2H+, which has the same critical density as HCO+, the N2H+ only traces the very high density region in the center of the cloud, and it's simply because of the sensitivity of the observations, right? It has a constant abundance, so this is a case where we are very carefully stacking to get the measured line ratios. So we use all of the data, and so this partially addresses it, but I agree with you that the brightness of the available lines biases us. Yeah, because I was just thinking if you, instead of normalizing your critical density plot, your Radex plots by the peak abundance, if you didn't do that, then you would see this dependence on the sensitivity. That's right, and I showed the overall sense of the variation here too on the left in the observed data for M51.
right? You can see that, for example, HNC is just crazy faint, right? And it's not necessarily because of a different critical density, it's just a lower overall abundance leads to a lower intensity and potentially biases us. The point is right, but we are trying very hard to stack to make a significant measurement and use measurements of everything everywhere, not to mask.
Thank you. Could you remind me, please, when you mentioned that the CO2 dust was rather constant in some measurements you did, what scales in the clouds were you probing?
Yeah,
and
so
what did you use for the dust? Because in local clouds, we definitely don't have a linear correlation.
No, that's right. So what we're using here is so for the Milky Way, we're using the Planck emission-based maps. And in the Magellanic Clouds, we're using the Herschel emission-based maps. We are hoping to shift this analysis as much as possible to use the HST extinction type maps over the coming years. But like I said, so sort of stay tuned for results from Karen Sandstrom's group on this. But it is a self-consistent treatment in the sense that we're matching the use fundamentally of temperature-corrected submillimeter emission. So the way to read this is that the CO emission at a given amount of submillimeter emission corrected for temperature is approximately fixed across these systems. The spatial scale, I think, is a bigger issue, and we've been trying hard to, so we've done multi-scale analyses now in the Milky Way. So this forthcoming paper is looking at the Planck maps and also attempting some incorporation of analysis of simulations in order to investigate the scale dependence. And you really do need to push to high spatial resolutions in order to have a prospect to resolve the low AV structure of the CO-AV relation, essentially because it's very easy to convolve bright stuff into empty space, and so blur out your relationship. So that the sensitivity of this kind of analysis to a threshold is extremely dependent on spatial resolution. But the bulk measurement here is actually already interesting and tantalizing, which is that what we can say is that the sort of twiddle AV of 1 integrated over a large spatial scale gives you about the same amount of CO emission in these 3 very different metallicity systems. So the span of a factor of 5 in metallicity, I think, makes this a non-trivial statement, although we would love to be at a parsec resolution.
Any more questions? Yes, Alyssa.
I have a question that's related to the last few. So in the plots that you showed that had M51 binned and M51 not binned,
That's right.
there was a lot of scatter.
That's right. So I actually like the way we're approaching this. So fundamentally what we're doing, we can measure roughly 2 to 3 sigma intensities in 100 hours with IRM on a galaxy. So we are leveraging the fact that we expect HCN and HCO plus to not exist where there is no CO. So we have beautiful CO maps for these galaxies, and we use these line profiles as a prior for where we would expect to find the dense gas. And then we have large amounts of area in the maps in the faint regions. And if we can formulate an experiment, so we think that HCN to CO depends on stellar surface density in this way, we can make, and the paper I actually encourage you to check out, we can make stacked spectra that individually have much higher signal to noise. So these error bars are from error propagation in this case. So these error bars on the red really are the statistical error bars on the stacked spectra here. So this is taking a large area in M51, sorting it by, in this case, H2 to H1 ratio, their stellar surface density, and stacking it up, and then measuring the integrated intensity there, using the CO as a strong prior on where we could find HCN emission.
Are you saying that someday you could have a model that would separate out the resolution, the chemistry, the sensitivity, all the things that could be giving you that big scatter region by region also?
Well, no. What I am saying is that we are trying to do the statistics right, and I could probably tell you how much of that is physical versus how much of that is statistical.
Right, but I'm asking a different question. I'm asking.
So, if I interpret correctly, you're saying you want to put multiple axes in here and make the hypothesis progressively more complex. We will run out of signal if we do that.
That wasn't what I was asking,
okay,
but
go ahead.
I'll ask you later. Never mind.
Yeah, so the general point is that this fundamentally does rely on stacks. We can model the physical scatter, but it requires averaging many lines of sight in order to do this while also mapping galaxies. We get the individual ones at a couple sigma. So as your hypothesis gets more and more moving parts, you will have to slice the galaxy or the data set more and more finely. And there's no way to get around, if we need fundamentally 8 hours of integration in a bin to measure this, then we need more data in order to test finer hypotheses. But the good news is that this is, it's somewhat terra incognita right now. And so people have not made maps of these lines in star-forming disk galaxies before. And so the sort of first order correlation analysis is still telling us things that are not written down in the literature right now.
Thanks, we need that.
Sure.
All right, we're going to move on. Thanks again, Adam.